So today we're going to talk about the effect of temperature on PV module. One of the first things you have to know is that as the temperature increases, the performance of the PV module drops. The efficiency of the PV module drops. So what is the cause of that? How does that happen? Most crystalline photovoltaic modules, most of the modules we have in the world today, except for the thin film modules, they do not perform well under excessive temperature, especially when the irradiance is constant and not increasing. So what you want to do when you are installing your photovoltaic module is to ensure that you do not have excessive temperatures on the module. This is very key. This is very important for you. And you know that as solar radiation increases, the temperature would also increase. If the temperature increases while the irradiance is constant, the current is increased. So this leads to a significant drop in the voltage. And one of the things we don't want to happen is that we don't want high current, low voltage, because this will lead to drop in performance. This is what happens. All the modules that we have, the solar cells, have charge carriers. They all carry charges, okay? So when you have many solar cells together, we have a module. That simply means that the module also, carry charges. So when the temperature increases, the charge carrier concentration and mobility would also increase. What usually happens is that the charges are actually held bound to their position. So as the temperature increases, the charges would lose from their position. They will be able to move, okay? So as the temperature increases, the speed with which the charge carriers would increase. That means they collide more. The more they collide, the more the mobility, the more there will be increase in temperature of the semiconductor, because the module itself is a semiconductor. As they move faster, they collide faster, and then there is higher increase in temperature. And when this temperature increases, there will be increase in current. When this current increases, that means there will be a drop in voltage. Now, when there is a drop in voltage, it affects the efficiency, it affects the output of the photovoltaic module. In many cases, you will find out that a small increase in current, look at it here, can you see that? A small increase in current can go a long way to lead to a large drop in voltage, as you can see here. So you can see that the current increase, the black line is the initial curve, the current voltage curve. I explained this in the previous class, in the previous teaching. The black line you're looking at here is the current voltage curve. So you will see that as the temperature increases from this black line to the red line just a little bit, you will find out that when you trace the red line down, the change in voltage is actually very large compared to the increase that we have in the current, okay? The open circuit voltage increases largely compared to the small and little increase in the short circuit current. All right, this is what happens when there is excessive temperature, or when the temperature increases in the module without increasing irradiance, or when irradiance is constant. The VOC, which is the open circuit voltage, is given with the expression that we have here. All right, so you can see we have our VOC, you can see we have KB is a constant, you can see we have a temperature, you can see Q here is a charge. We have lane of JPH, we have J naught. J naught here represents the current prefactor, and then +1. So what you find out here is that the J naught strongly depends on the temperature of the module, okay? The most important thing for you to know here is that we have to watch our design, and then we have to install our system in such a way that the temperature will not increase with a constant irradiance. If this happens, it leads to increase in current, drop in voltage, drop in the performance of the system, drop in the efficiency of the module, and eventually drop in the entire efficiency of the power plant. All right, let's take it a step further. Temperature coefficient of voltage is the rate of change of voltage and output power with temperature. What this means is that it is possible for you to have your current voltage graph, and then when you plot the graph of your voltage, VOC here, all right, against your temperature, this is VOC, and you plot that graph against your temperature, all right, this is what you're going to have. Voltage against temperature is going to look like this. As the temperature increases, this is 0, this is the initial point. So what you see here is that as the temperature increases, you can see that the voltage is dropping. As the temperature is increasing, the voltage is dropping. In this particular case, what you're going to have here, your temperature coefficient is given as the x dt. That's the rate of change of voltage. All right, this is what you're going to have as your temperature coefficient, much more like the slope of the graph. So the x dt will give us the rate of change of voltage with respect to temperature, where x in this case will be equal to VOC. All right, x in this case will be equal to the open circuit voltage. Okay, so we can have this particular scenario. Then there is another scenario we can have. Apart from having a rate of change or voltage with respect to temperature, that gives us a particular temperature coefficient with respect to voltage. We can also have temperature coefficient with respect to power. That will be rate of change of power with respect to temperature. In that particular case, this is what you're going to have. You're going to have a graph that looks like this. So that means you're plotting the graph of power, right? The graph of power against your temperature, if you have that. Again, the graph is also going to come down too, but not as steep as what we have in the voltage. Okay, so what you have here is that as the temperature also increases, what happens to your power? The power also decreases. So this is what we don't want when we install our PV system. As the temperature increases, the voltage will decrease and the power will decrease. In this particular case, we have the x, the t. This is going to be the rate of change of power. All right, so that would mean our x in this case would be equal to power. All right, so we have the rate of change of power with respect to temperature. So this gives us temperature coefficient with respect to power here, and then we have temperature coefficient with respect to voltage. You need to know these, and you need to know how these affect the performance of a system. All right, so if you're given this kind of a graph, you should be able to interpret it just the way I just explained it right now. Let's take it a step further. What does x of t mean? X of t would mean, x here would mean power at temperature T. All right, what is the power when we have this particular temperature? In other words, we can estimate the power we would have when we actually, are given a particular temperature. Okay, we can find the output power. So in this particular case, we can say, okay, we have a standard temperature, which is usually our TSC. This is standard test conditions temperature. All right, so this is standard test condition power. This is a power at standard test condition. That's why we have STC here. STC means standard test condition. So this is power at standard test condition. Okay, it could also mean voltage, like I explained to you with the two graphs that I drew for you and I explained. Okay, so it could be voltage against temperature, or power against temperature, or probably even current against temperature. All right, so what you see here is that if we say x is equal to P, which is equal to power, so this becomes power at temperature T, this becomes power at standard test condition, these become the rate of change, this becomes our temperature coefficient, this is the x to T now becomes our temperature coefficient. All right, rate of change of power with respect to temperature, and then this T would mean the new temperature that we're looking for. This T will be the same T that is here. Okay, it will be the same T that is here. All right, and then minus the standard test condition temperature. So in many cases, you usually have the standard test condition temperature, and then they tell you that as standard test condition, this is the power rating, this is the nominal rating of the PV system as standard test condition. So all of those will be given to you. They would also give you the temperature coefficient. So they will tell you or ask you in your projects or in your questions or exams or quizzes that, look, if we increase the temperature of the system, let's say from 15 to 20, from 20 to 25, from 30 to 35, what would be the power output? Will the power output increase or decrease? So if you are faced with a situation like that, this is one of the expressions that you can use to actually analyze such project or such questions. All right. So what you can see here is TCL usually represents tolerance. As you can see here, this TCL usually represents tolerance. So this will be the tolerance of open circuit voltage minus 0.33% per Kelvin. This is the tolerance of short circuit current, minus 0.004% per Kelvin. Tolerance of power, as you can see here, and then you have the NOCT. NOCT represent nominal operating cell temperature. I'm going to tell you, a little more about that as we go on. NOCT means nominal operating cell temperature, and the entire table you see here represents the measuring of tolerance for all data at plus or minus 10%. Let's take it a step further. So in case we have a situation where we want to examine temperature effect, let's say that the power at standard test condition, or the rated power at standard test condition, is given as 250 watts, right? And then they gave us the PDT. The PDT now would represent the temperature coefficient with respect to power, all right? Temperature coefficient with respect to power, or that is the rate of change of power with respect to temperature. Okay, those are two ways to put it. So we are given the P to T as minus 2W per degree Celsius. And then we are given the standard test temperature as 25. Actually, standard test conditions, let me quickly show you this. Standard test conditions, temperature is usually equal to 25 degrees at standard test conditions. At standard test conditions, the air mass, AM, is usually equal to 1.5, all right? At standard test conditions, the solar radiation, irradiance G, is usually given as 1,000 watts per square meters, all right, at standard test conditions. So we have all of these as standard test conditions, all right? Here we have been given temperature at standard test conditions with 25, we take it as 25. So we are now asked to find the power when temperature increases from 25 to 30 degrees Celsius. What will be the power when temperature increases from standard test conditions 25 degrees Celsius to 30 degrees Celsius? I already told you the formula you're going to use. With respect to power, that means we are looking for power of 30, power at 30, that's P of T. If you look at the previous example given to you, you see that power at 30 will be given as power at STC, right? That's what's supposed to be. It will be power at STC plus the temperature coefficient, this becomes the PDT now, then multiply it by change in temperature. It becomes very easy for you to find power at 30 degrees Celsius. Also, power at standard test condition has been given as 250. Okay, the power at standard test conditions has been given as 250, you just put 250 here. The PDT has been given to us as minus 2 watts per degree Celsius, you put that here. 30 minus 25 is here, this becomes 5. So if you carry out the arithmetic operations there, you will obtain power at 30 degrees Celsius to be equal to 240 watts. What did you observe here? You will find out that the power has dropped from 250 watts to 240 watts when the temperature increased. So if the temperature increased much more than 30, it's possible that you keep losing power and then the power keeps dropping. It keeps dropping. And this is what we don't want. So your duty when you are installing, when you're carrying out your installation of a PV power plant, a PV system, is to ensure that you prevent these losses as much as possible. And a lot of factors will go into trying to design a PV that would minimize all of these losses, that will minimize temperature increase, unnecessary temperature increase, thereby increasing the current in the module, thereby reducing and decreasing the output power and output voltage or open circuit voltage of that particular module. So your design characteristics have to be top notch and on point. At standard test conditions, T equal to 25 degrees Celsius. That is constant, all right? At NOCT, at nominal operating cell temperature, I'm going to mention that later, T is equal to 20 degrees Celsius at NOCT. At NOCT, nominal operating cell temperature conditions, our T in this case would be equal to 20 degrees Celsius. Our G would be equal to 800 watts per square meters, all right? So you can see that there are some variations here. So at nominal operating cell temperature, these are the values you have. At standard test conditions, these are the values that you have. We will talk more about these in upcoming teachings. AM stands for air mass, and then the same formula I showed you is the same formula you're going to use If you are given temperature coefficient with respect to voltage, you will use the same formula. That simply means you are looking for the new voltage when the temperature increases, or you are looking for the new current when the temperature increases. You're going to use the same formula. So you could be given temperature coefficient with respect to power. You could be given temperature coefficient with respect to voltage. You could be given temperature coefficient with respect to current. You could be given all of those. When you have those, that simply means you're going to be given the standard test condition voltage, and you can use that to find the new voltage. Or you could be given the standard test condition current, and then you can use that to find your new current. All right. So this is just to further explain what I already explained to you guys. Effects of temperature on the PV module. So when the temperature increases, what do we do when we have excess temperature on PV module? What do we do when we have excess temperature on PV module? There are several things you can do, all right? One of the things that I believe has been researched and implemented is to have a PV thermal. In some cases, there are ways you can help cool the system. So in that way, you can have a PV thermal system. Instead of losing the efficiency of your system, you can increase the efficiency of the PV system when you convert it into a PV thermal. It is usually called a hybrid PV thermal power plant. All right. What happens in that particular situation is that the heat that is generated when temperature increases, that heat is collected and then used for other things. So a heat exchanger or a way of collecting the heat will be incorporated into the system, and that heat will be directed somewhere else where it can be useful as heat energy for some other things. All right. That way you would have increased the efficiency of the system, because you will be producing both electrical energy and heat energy from the PV system if you can do that. That way, the efficiency of the system would increase instead of losing efficiency because the system is too hot and then the module is degrading or it's reducing in its efficiency. All right, that's one of the things you can do. Look at what is going on here. Sometimes you could actually, make sure the PV system experience cooling, proper cooling. All right. So if the PV system is installed in such a way that it has proper ventilation, it simply means that when the temperature increases and the PV modules are hot, the air underneath the module can actually cool the system. Okay, so several ways via which you can actually ensure that the temperature of the system does not cause excessive heating, because when temperature increases, the heat produced will increase because of the collisions, multiple collisions of the charge carriers in the module. Heat will be generated. This leads to increase in current, and then this leads to drop in voltage. That heat, we can collect it, and when we collect that heat, it simply means that the module is not hot. All right. So there are several ways. For example, this is a sun. This just show you that there's a sun here that is heating the module. Okay. As the sun hits the module radiates heat to the environment. Okay. It has heat, and this heat can be radiated to the environment. When that happens, the module is just going to make use of what it wants to use from the sun, which is the solar energy, convert it to electrical energy, and then instead of the system to be excessively hot, it won't be hot. The heat is going to be radiated to the environment. All right. Also, we have what we refer to as convective heat transfer caused by wind across the module. This is what I was referring to as the cooling due to convection. All right. So when the sun hits the module and then the module becomes hot, there is a way the air around the module can actually transfer the heat on the module somewhere else. Okay, so if you build that properly and there's proper ventilation, the module is going to be cooled via convection. That is possible. The module can also be cooled via radiation. Also, we have conductive heat loss by heat flow from one material to another. So heat exchange depends on ambient temperature. What is ambient temperature? Ambient temperature is the same thing as the air temperature. So heat exchange depends on the air temperature. It also depends on the wind. When there is enough wind, that simply means that cooling can be faster. When the ambient temperature is not too hot, then radiation is going to be faster, because that simply means that the heat is going to move from region of higher temperature, which is going to be on the module, to region of lower temperature. But if the environment is very hot, the ambient temperature is also very hot. That is, the air temperature is very hot. As the heat is increase on the module, there is no place the heat is going to be exchanged to. Okay, so that becomes difficult. All right. Then the U value, the heat exchange also depends on the U value and the thermal conductivity of the module. So we have the NOCT model, nominal operating cell temperature model. Apart from the standard test conditions model, we have the nominal operating cell temperature conditions model, basically. So in that particular case, our wind speed is 1 meters per second. Solar radiation is 800 watts per square meter, like I mentioned earlier, which is our G. Ambient temperature this time around is going to be 20 degrees Celsius. So if you want to find the temperature of the cell, okay, if you want to find the temperature of the cell, this is the formula that you're going to use to do that. Ambient temperature is usually given. We know that as 20 degrees Celsius. You could also call it air temperature. G is always given to, we know that as our 800 watts per square meters under NOCT conditions. Then we have the NOCT temperature is given here. You'll be given the NOCT temperature, all right? And then you have the 20 degrees Celsius here as the ambient temperature. This is very important. And then you also have your G here, which is the solar irradiance, 800, all right? So with this, you can actually calculate the temperature of a particular module at a given temperature. So some important points I'm going to quickly call your attention to here that you must note. I've been mentioning it over and over. So again, let me call your attention to them. The open circuit voltage is usually called VOC decreases as the temperature increases. We don't want that to happen. Okay, but this is what happens when temperature increases. The maximum power decreases as the temperature increases. We also don't want this to happen because this reduces the efficiency of the system. Eventually, it reduces the output, the amount of power we can get from the module or from the PV system or power plant. Then the current, maximum current and maximum power decreases as the temperature increases. So when temperature increases, it's not a good thing for the PV system as the temperature increases excessively. Right, let's take it a step further. This is a chart. This is just a chart you can look at. Most of the time, these values come with the module. Okay, at the back of every module you see, they will give you the STC values. Some will give you the thermal data. They will give you the NOCT values. All right. So if you pick a particular module up, a standard test condition, which is 1,000 watts per square meter and 25 degrees Celsius, and air mass of 1.5. All right. You will see for a particular module, depending on that module and the manufacturer, the power rating here is 320. I want you to follow me. You can see that we have different power ratings here. Okay, so each column represents a module. Okay, so this is a module of 320 or peak watt. All right, this P here stands for peak. This is 320 watt peak. All right, this is 315, another module. This is 310, another module. This is 305, this is 300, this is 295. And then you can have modules of 200, 215, 250. And now I think we have modules of up to 400 now, or 415. But let's say that we have a module looking at just this column alone. First of all, just this column. Okay. So what you see is that the maximum power is 320 watt, which is rated power of the module, is usually rated on it. The module efficiency is 16%, as you can see here. You can see we have the rated voltage, VNPP 36.8, rated current is here, open circuit voltage is given, short circuit current is given, the maximum reverse current is given, maximum system voltage is also given, as you can see here. These are other data using the NOCT model, all right? So you see that for the same module, at NOCT model, using NOCT model, the power rating has dropped. Okay, a couple of other things have dropped right down to the short circuit current. And then you can see we have the thermal data. These are the thermal data here. Thermal would mean coefficients. Okay, so with respect to voltage, coefficient with respect to current, coefficient with respect to power, and so on and so forth. All right, and you can see we have the NOCT, which is 48 degrees Celsius plus or minus 2 degrees Celsius. The thermal data will be applicable to any of the module. But I had to show you this so that you can know how to read this data off your PV module in case you have to work on a project and you have to use the PV module. This is the production line of a module. Okay, so you probably just want to look at it and have an understanding. Okay. There are several parts to a module. The module has a frame, the module has a glass, the module has solar cells, which are semiconductors. The module also has some laminations. Okay, so quite a number of components on the module. So if you want to produce a module, this is the line, okay? They first of all wash the glass. From washing of the glass, they string the glasses together. From there, we have what we refer to as the folio handling. And then from there, we have the lamination. They laminate the module, they laminate the module, you know, to laminate the glass, they cover it for protection purposes to ensure that the module is protected. We have the glass washing, they string the glasses together, then we have what we call folio handling, the lamination, then the framing. Each of the modules have framing by the sides. Okay, they frame the modules, all right? So we have module simulation and quality inspection. We have to, you know, inspect the module to see that it has proper quality. And then from there, we have module separation. As you can see here, many modules are already in here. At this particular point, they begin to separate the module. So you have one module goes here, it keeps going there. You have different modules, and you know, until you have as many modules produced as much as possible. All right, let's go on. So mode of operation of a standalone system. We've talked about the mode of operation of a standalone system before, so I'm just going to quickly go through these. A standalone system is also referred to as another grid photovoltaic system. So this is your PV array. A standalone system means it is off-grid, and that would be interpreted as not connected to the grid. It's standalone because it's not connected to the grid. It's not connected to the utility grid. If there is no sun, it simply means that no energy can come in, except we have a storage facility. And that is why all standalone machines they usually have battery bank if you must keep providing power from your PV when the sun is not shining. So they usually have a battery bank, and then the battery bank stores electrical charge. All right, we have the charge controller here that ensures that all the you know, circuit parameters are respected, and it also ensures that the battery is not overdrawn or overcharged. Then we also have what we refer to as the standalone inverter. What the standalone inverter does is to convert the DC energy to AC electrical energy. And before the conversion happens, if you have DC loads, you can also always connect your DC load before the conversion takes place. Because once the conversion takes place, what comes out of the standalone inverter is going to be an AC electrical energy. So the AC electrical energy is what will pass on to our AC load via the distribution panel. It's passed on to the AC load of the user. And if the user has DC loads, they connect the DC load to the system just before the standalone inverter conversion takes place. All right. So you can see we have our loads here, we have the PVR, and then we have the balance of system that contains all the other components and connections that are needed between the production and then the use of the energy that is being produced. The inverter that supplies AC power to the load has to appear as a voltage source with a stable voltage and frequency. This is very important. For a grid connected system, which we can also refer to as an on-grid PV system. In this particular case, there is a grid here. As you can see, there is a grid here. This grid represents the utility grid. In Cyprus here, the utility service provider is referred to as the keep tech. For some of you who have lived in Cyprus, the utility service providers is referred to as keep tech. So that simply means if you are connecting to the grid, that means you are connecting your PV to keep tech services. All right. So in this particular case, what you would have is you have a PV area as usual. The PV area generates electrical energy from solar energy, from the energy of the sun. The PV converts energy of the sun to electrical energy. This electrical energy is usually DC energy, as I mentioned earlier, DC energy. So this DC electrical energy is passed through a grid connected inverter, as you can see here. This is a grid connected inverter. What this inverter does is to convert the DC electrical energy to AC electrical energy. Now, in this particular case, what you would find out is that once the energy is converted to AC, the AC energy is then transported to the grid via the distribution panel or to the users via the distribution panel. This is very important because in many cases, you know, your PV will produce more than enough energy. When you have more than enough energy, it has to go to the grid. When you don't have enough energy, you collect from the grid. That is the advantage of the grid connected system. When it is connected to the grid, please pay attention to this. This is very important. Listen closely to it. For the grid connected system, when you have excess power, excess energy provided or produced by your PV generator, the excess energy, after you have taken the ones you want to use, the excess energy that you have is sent to the grid. So in this particular case, you will notice that there is no battery here. We don't use battery here. In this particular case, the grid is acting as a temporary storage. It's acting as a temporary battery. It's not a battery, but it's like a storage facility for the energy you send into them. In countries where there are proper incentives, the energy you stored in the grid is going to be recorded. There's going to be a meter that records all the energy that you send to the grid, so that when the day comes that you don't have enough sun, or in the night when there is no sun and your PV is not generating any power and you must use power in your load, whatever energy you have sent to the grid, you can collect it back. It can be drawn back and then you can use it. So that simply means in this particular case, you are using the energy from the grid, but you will not be paying for the energy you are using from the grid if you collect exactly the amount of energy that you sent to the grid, or you collect lower than the energy that you have sent to the grid. Because when you had excess, you sent it to the grid. Now that you need power for your load and your generator is not generating, your PV is not generating any power, whatever it is you have sent to the grid is what you collect back and then you use. In that case, you won't pay the grid. You won't pay for electricity because it's like it was just storing your energy for you. But if you draw more than what you have saved, for example, if you send in 20 kilowatt hour and you draw 30 kilowatt hour, you will only pay for how much? You only pay for 10 kilowatt hour because you sent in 20, you took 30. You just net the 20 you sent in from the 30 you have used, you have just 10 left. That means you're only going to be paying the utility services for just 10 kilowatt hour. This is very important. You need to understand how it works because there are some countries that have what we refer to as some incentives when you generate excess energy with your PV system and then you send them to the utility grid. They have incentives for that. The incentives could come in terms of the feed-in tariff, it could come in terms of net metering, it could come in form of green certificates, it could come in so many forms. All of these we'll talk about as we move on. All right. So the inverter latches on the grid frequency and voltage. The inverter's main task is to pump power to the grid, okay? So it has to latch to the frequency of the grid. This is very important. The inverter that supplies AC power to the grid acts as a current source, okay? So in the off-grid system, the standalone inverter acts as a voltage source. In the grid-connected inverter or the on-grid connected PV, the inverter or the grid-connected inverter acts as a current source, while the role of the voltage source in the system is fulfilled by the grid. So this is a hybrid system. I mentioned in one of the teachings we had recently, but one of the previous teachings, if you check the other links that I provided, you will get them. You could have a hybrid PV system that combines both the on-grid and the off-grid together, okay? So what can you see here? What you will find out is that we still have our PV array, we have our battery bank, and at the same time, we still have the grid, okay? Now, it's difficult to do this because it's going to be expensive, but if you can do this, this is good for you, all right? So we have our charge controller. Once there's a battery bank, there's going to be a charge controller here because the two of them have to work together. Then you have a bimodal inverter. A bimodal inverter is an inverter that can serve as a grid-connected inverter and at the same time stand as a standalone inverter, all right? And then we have our distribution panel as usual. Then your AC load is here and you have your DC load here, okay? So it's possible for you to have a hybrid system. A hybrid system is two systems, you know, that can be used independently, separately, brought together, designed to work together, all right? And this has a lot of advantages, a whole lot of advantages, but it's expensive. That is why this is not usually patronized, except if you have a very small system. But for large systems, this is going to be very difficult. The PV system is capable of functioning either as a standalone system with the battery storage or as grid-connected system. It can be in both modes. In standalone mode, inverter behaves as an AC voltage source. In grid-connected mode, the inverter would behave as an AC current source, as we explained earlier. This is the end of this particular session. Thank you for watching this video till the very end. I'd like you to subscribe to this channel so you can help keep this work going on. And if you like this video, please give it a thumbs up. I have a simple question for you, and I would love to read from you. Here's the question. Do you think renewable or alternative energy technologies can take over the conventional fossil fuels technology, such as the oil and natural gas? Please drop your answer in the comment section. I'd like to read from you. See you in the next session.